Hello and welcome. And hello from snowy, chilly Walla Walla. We're experiencing, like most of the rest of the country, some very below normal temperatures. Um, I will just put in a plug right now for retired geology professor Kevin Pogue has started a really great Facebook group called Walla Walla Valley Earth Sciences. And he's doing a great job explaining the weather in the valley and has actually been pretty great about his predictions this season, especially about when we will or will not have that inversion layer of fog. My name's Jennifer Northam, and I am the director of our Alumni Relations Office and also a graduate from the class of 91. And I am thrilled to have you all here today from wherever you are coming from. I just want to give you a quick campus update. Students have been back on campus from winter break for about 3 weeks. And boy, you can tell that they have started to buckle down and get serious about school again. Um, but also, winter sports are about to wrap up and spring sports are well underway. The swimming teams will face the conference championship meet this weekend in the Seattle area. Women's basketball is currently ranked number 5 in the nation and are really powering through. I mention that in particular because I know Bob and Claire Carson are huge fans of the basketball team. So wanted to just give a little plug there. Uh, we should have a magazine from the communications office arriving in your mailboxes soon, and there are some great stories this time. So hope you'll read it from cover to cover, as usual, I assume. Uh, Okay, we've kind of slowed down on people joining us. I'll just let you know that this presentation is being recorded. And if you would like to leave your camera on, we would love to see your faces. I know in particular that Bob appreciates being able to see former students and some colleagues. So that's great, but if you do not choose to have your camera on, that is fine. When we get to the questions portion of the presentation, I will be happy to take your questions in the chat and give them to Bob, or you can turn on your camera and ask them yourself. Any way you want to get that information to us is just fine. I just saw Peggy asking about the Facebook page, and I will indeed put that in the chat. All right, so it's my pleasure today to introduce someone who probably doesn't need introductions, but I'm going to do it anyway. Bob Carson, Grace Farnsworth Phillips Professor of Geology and Environmental Studies Emeritus. After earning his undergraduate degree at Cornell University, his master's at Tulane University, and his PhD at the University of Washington, Bob taught at North Carolina State University and the University of Oregon before joining the faculty here at Whitman in 1975. Bob split his time between the geology and environmental studies programs, combining his expert knowledge of late Cenozoic geologic history, oh man, I knew I was going to do that, surficical processes, and Bob, you can correct me later, and landform evolution with his curiosity about resources, pollution, forests, and oceans, and the impact of climate change on all of these. As you can tell by the number of attendees on this Zoom, we're at 149 and counting. Bob was a beloved professor during his 40 years at Whitman. He was also a dedicated supporter of the Whitman Outdoor Program and led decades worth of trips, impacting the lives of students both in and out of the classroom. I should note that he was often accompanied by his wife, Claire, herself a member of the Whitman staff for 38 years and continuing member of our close community. Bob retired in 2015, but has continued to lead trips, publish books, and give lectures around the country and around the world. Those students are now generations of alumni who have continued to adventure with Bob and Claire. We're honored to have him here today to discuss earthquakes and tsunamis in Western Washington. Bob, I am happy to turn the program over to you.
Thank you, Jennifer, for inviting me to make this presentation and for that very nice introduction. On this screen, you can see a map and a cross-section of Western Washington. We live on the North American plate. To our west is the Juan de Fuca plate, and farther west is the Pacific plate. The seafloor is growing. There is spreading or divergence going on at what's called the Juan de Fuca spreading zone. And that seafloor is moving east to a convergence zone where that seafloor, both basalt rock and sediment, is going underneath North America. I'll say a little bit more about plate tectonics of Western Washington later. So let's see, Jennifer, I hit the button to make this go forward and it's not going forward. So I'm doing something wrong. While we are waiting,
I'll be right there.
I'd like to tell you a little bit about my fault experience. You will hear, meaning earthquakes. You'll hear a lot about it in this presentation. I also did research on active faults in Mongolia, and my chief scientific partner there was Carl Wigman at North Carolina State University, where he has the position I held in the early 1970s. We did research with Whitman students, other students from Mongolia and the United States, and with other professors in Mongolia on 5 separate occasions. Thank you, Jennifer. A lot of the information that you will hear and see today is from publications by the Washington Geological Survey based in Olympia and by the United States Geological Survey. So here's what's going on between that Juan de Fuca plate and the North American plate. It's building mountains. It's making the volcanoes with which you are so familiar. There are inland earthquakes, and by inland, I mean, for example, in the Puget Lowland, they are typically about magnitude 7. They can cause tsunami in Puget Sound, and they definitely cause landslides. In contrast, we also have earthquakes generated just off the coast. These are likely greater than magnitude 9 based on what we know and from what happens elsewhere around the world. And those big earthquakes generate landslides. They make huge tsunami on coasts, and they can make small tsunami inside Puget Sound. My dissertation was on the glacial geology of the Olympic Peninsula. I was focusing on the south central Olympic Peninsula and looking at the relationship between glaciers going south out of the Olympic Mountains and meeting with glaciers going southwest. These glaciers had come all the way from British Columbia. The Star is where I almost accidentally discovered Washington's first known active fault. Every winter, in the winter of '73, I was still at North Carolina State University, and I had hundreds of aerial photographs, and I was looking at them to try to figure out what to do the next summer. If you know the area, this is Lake Cushman in the southwest, and Hood Canal is off to the east. This is Price Lake. This is Saddle Mountain. You'll hear that name often. This is Lilliwap Swamp, and these two ponds are in a straight line with the east end of Price Lake. I suspected this is a lineament. This is a line. A lineament can mean anything. It could be a highway, a railroad, it could be a fault. I suspected this was a fault, but the trees were covering it pretty extensively. So I asked the state of Washington to give me the oldest air photo, which was from 1939. This is what came to be known as the East Saddle Mountain East Fault. There's a pond here, and there's a pond here, and there's the east end of Price Lake. With the old air photos, we were also able to discover another fault, which became the Saddle Mountain West Fault. I won't say very much about it, except that there's a hint based on radiocarbon dates from Lilliwap Swamp, which lies immediately east of this fault, that last moved about 5,000 years ago. So I knew from that on this fault that because the drainage is to the east, that this side of the fault had to be up. But that's about all I knew. And I also was pretty sure that it was post-glacial because it interrupted the topography that had been left behind the glaciers about 15,000 years ago. So I took first North Carolina State students and then Whitman students to study the glacial geology and the faulting of this area. This is a fault scarp. The far side has gone up and we are standing on the side that has gone down. I had no idea whether it was a normal fault, this is sort of what the topography looks like, or whether it was reverse fault, which would have similar topography because the part that went up would collapse onto the lower part. Later, we'll talk about strike slip faults like the San Andreas Fault in California. So it seemed like the best thing to do was to dig a trench across the fault. Here are my oldest sons, very happy to watch the front end loader and bulldozer excavate this trench across the fault. This is the fault that we discovered in that trench. The contact between the glacial deposits and the bedrock is there on the upthrown side and down here on the downthrown side. So we know that it is a reverse fault. The part that went up is overhang and collapsed onto the part that went down. So I know that the fault is post-glacial, younger than about 15,000 years. And I looked for the biggest trees on the fault scarp. This one presumably died when this area was logged in 1925. And by counting the rings, I knew that it was born in 1790. So now I know that the fault is older than the year 1790. Immediately, there was one of many, many papers that have been written over decades on this particular fault. And lo and behold, as we looked across Price Lake, which had to be dammed by the fault, we discovered that although Whitman students walk on water, there were stumps of old growth Western red cedar on the bottom of this lake. There's one of them. So let's go in the lake and see if we can bust the outermost part of this stump off. We did this in several places, and the radiocarbon dates came out to be approximately 1,100 years ago. Now I'm going to switch gears for a minute and show you modern LIDAR photos. They are good. LIDAR is a type of radar in which you subtract the elevation of trees and buildings from the ground. So we're looking at the relief of the ground here with less than a meter. The Saddle Mountain East Fault extends into the forest, and if you try to walk here today, you can't even find it, but it shows up prominently on LIDAR, may be present up here, and may extend all the way over to Lake Cushman. Let's now change gears and go east to the Seattle Fault, which runs east-west and is upthrown on the south side. An earthquake approximately 1,100 years ago, based on radiocarbon dating, was associated with uplift of the Seattle Fault, so that Restoration Point had a shoreline here, but when there was uplift, the shoreline was a lot further away. New land was generated. These sedimentary rocks are quite erodible, so in the last 1,100 years, the coast has retreated to the line labeled B. So what do we know about the Seattle Fault Zone? We know that it has generated earthquakes that average around 6.5, sometimes higher. And we know that these motions, because they are up on the bottom of Puget Sound, generate tsunami, which would hit Seattle in about 3 minutes after the fault moved. The inundation could be as high as 42 feet, and there would even be inundation to the south in Tacoma. There were probably other landslides, other tsunami generated by landslides. What does this word tsunami mean? Translated from the Japanese, it means harbor wave. It is sometimes improperly called a tidal wave. It's important to emphasize that this is not a single wave and that it doesn't always only go up. It goes up and down like most waves do. And there can be many waves with periods between the waves hitting the shore of minutes to hours. So it's caused by a displacement of water. Again, I want to emphasize the fact that the land under the water has to go up or down. So that's only due to normal and reverse faults. It would be very rare, almost impossible for a strike slip fault to generate a tsunami. We also get tsunami from landslides, from volcanoes that are at near sea level, from big icebergs calved off of glaciers, and from meteor impact. The wavelength and the height of the tsunami is dependent on the water depth. Very, very low at sea and can be very high when it comes onto the land. This is an example, a model of having an earthquake on the Seattle Fault and sending a tsunami down south in Puget Sound, and how much of the city of Tacoma would be inundated. So let's now compare these two Puget Lowland faults, the Saddle Mountain East Fault and the Seattle Fault. And the methodologies I'll use here will be in terms of when it happened, dendrochronology tree rings, and trying to estimate the magnitude of the fault or the area of the fault that ruptured, fault length times the scarp height. We believe that the Saddle Mountain East Fault generated earthquake of magnitude about 7.3 to 7.5. And we know from the dendrochronology, the detailed study of tree rings just in the past few years, that it occurred in the winter of 923, 924. We were very surprised to find that tree ring studies on the Seattle Fault indicated that it occurred the same winter and had approximately the same magnitude. And as I said earlier, because it occurred underwater in part, it probably generated a tsunami. The people that wrote this paper, which is summarized in the journal EOS, suggests that if both of these faults moved at the same time, it was a 7.8 earthquake. Let me say a little bit about magnitude. I'll say a little bit more about it later, but the fact that two faults moving that are 7.5 or less can generate a much, much larger earthquake because it's a logarithmic scale is quite significant. So when Richter invented the earthquake magnitude scale, he designed it for a log scale base 10, but he didn't know about all the energy, particularly the long waves. And so the actual energy released on a log scale is the base 30, meaning that a magnitude 8 earthquake releases 30 times as much energy as a magnitude 7 earthquake. As I think I hinted before, the inland earthquakes are typically magnitude 7, whereas subduction zone earthquakes may be magnitude 9 or higher. If you multiply 30 by 30, for going from magnitude 7 to magnitude 9, you can see that the energy release is 900 to 1,000 times as great. This map and cross section mentions the 1872 earthquake, and as well as the subduction zone earthquake of the year 1700 that I haven't talked about yet, and of other earthquakes that are a little bit deeper and are inland and are typically of magnitude 6 to 7. I'd like to go over 3 or 4 historic earthquakes in Western Washington, and then I'll go to the San Andreas Fault. So the 1949 Olympia earthquake was felt throughout the Pacific Northwest. The damage in today's dollars would be more than $1 billion. There was damage, in pretty significant damage, all over Western Washington. The 1965 Tacoma earthquake of approximately the same magnitude lasted for 10 to 20 seconds Unlike most earthquakes, it did not have any aftershocks. Aftershocks are typically small earthquakes after the main earthquake. There was a lot of damage, and that amounted to only $12.5 million, but that's in 1965 dollars. And then we have the 2001 Nisqually earthquake, magnitude 6.8, which I expect most of you remember. Its duration was nearly a minute, which is a lot of shaking. The damage was $2 billion, and there was damage to a lot of places in Western Washington, including transportation related damage like the airport and the ports of Seattle and Tacoma. Here's a map of world plate tectonics, with which I expect you are familiar with. We have convergence all along the East Pacific Rise, and then we get strike slip motion, sideways motion on the San Andreas Fault. We come up to the Juan de Fuca plate, which I mentioned is going eastward toward the North American plate. Then there's a strike slip fault along the Queen Charlotte Islands, and we go up to a subduction zone or convergent plate boundary at the Aleutians. I want to talk a little bit about the San Andreas Fault because its magnitude at approximately 8 was roughly the size that we can expect from some Puget Lowland earthquakes. The absolute motion of the North American plate is west-southwest based on what's called the Yellowstone Hotspot Tract, which is the Snake River Plain. And the absolute motion of the Pacific plate is west-northwest based on younger Hawaiian volcanoes being to the east-southeast. So those are absolute motions, but these two arrows show the relative motion. Notice as you look across the San Andreas Fault in either direction, that the side to the right, that the far side is going to the right. Here is the San Andreas Fault, where it is perhaps most spectacular in Southern California. Again, the far side is moving to the right. The near side is moving toward Alaska. This is the New York Times from April the 19th, a day after the San Francisco earthquake. Current estimates of its magnitude are 7.9. Its rupture length was quite long, 300 miles. More than 3,000 people were killed, although the city of San Francisco only admitted that 650 people had been killed, but later research with tombstones indicates that the death toll was a lot higher. The fire was so bad because gas mains broke from the earthquake, and this caused sparks, which caused fires, but the water pipes broke, so they couldn't put out the fires. I'd like you to consider this magnitude of earthquake when you're thinking about the Puget Lowland. There was noticeable shaking for a wide area from north to south. Notice that these zones of relative intensity are stretched out along the San Andreas Fault, which ends right up here at Cape Mendocino, where we get into the Juan de Fuca plate, but it goes far to the south, all the way down to Baja California. These are just a few pictures of the damage from the great earthquake in San Francisco. Now I want to talk about the 4 largest earthquakes in historic time from 1900 until present. As it says at the bottom, I want you to think about these earthquakes that have occurred in historic time, because the next one that occurs along the Cascadia subduction zone and what we know about past earthquakes on the Cascadia subduction zone is going to tell you something about the shaking and the tsunami. They were all shallow. They all lasted a long time, probably greater than 4 minutes. They were all where there is convergent plate tectonics, like the Juan de Fuca plate going beneath the continental plate, and they all caused ocean crossing tsunami. So I'll go across these 4 through time, and I want you to notice that in general, And this is just a coincidence that they were larger in 1960 and smaller in 2011. So here are the Andes, which in many places are volcanoes. Here's the Nazca Plate, which is overlain by the Pacific Ocean, going beneath the western edge of South America. We get not only earthquakes, but we get tall volcanoes and high mountains. Not all of the mountains in the Andes are volcanoes. This is Valerica. I chose this picture because it is so beautiful. That's a fairly recent eruption. I want to pause for a minute to mention one particular outing by Whitman students and alums, these have occurred all over the world and were not necessarily associated with the outdoor program. Some were associated with classes that I was teaching, and many have been with alumni. So our goal was to take a look at Aconcagua, which is the highest peak in the Western Hemisphere, and to see both the south face and the west face from different places. Another goal in this 1 week backpacking trip was to climb the peak Cerro Benite, and it's from that summit that we got this good view of the west face of Aconcagua. Okay, back to earthquakes. The Great Chilean Earthquake, the largest one since the year 1900, magnitude 9.5. Four foreshocks, which were a warning that an earthquake was likely to happen, and which made a lot of people do things to make it less likely that they would die. And this is fairly unusual with earthquakes, period. But 2 days later, a volcano erupted in the Andes. The upper picture is of that volcano erupting 2 days after the earthquake. And the lower picture is another one that I chose just because it is so spectacular, a more recent eruption in 2011 of that volcano. Now we'll go to, this is Chile in 1960. Very long fault displacement, over 500, almost 600 miles. The damage was from shaking, subsidence, about which I will say a lot more later, and the tsunami. The duration was a whelming 10 minutes, if you can imagine that much shaking. The epicenter was at a town, Valdivia, which is sometimes the name of this particular earthquake. The tsunami in Chile was up to 80 feet high. It affected most of the ports for the entire length of Chile. There was a tsunami in Hawaii that was up to 36 feet high. And the tsunami, these are hours right here, hit the Philippines about 23 hours after the earthquake and killed people there. This is some of the damage, mostly or maybe entirely from the earthquake in Chile. Now we'll move on to the Alaskan earthquake, also called the Good Friday earthquake, from the 27th of March in 1964. It also was way over magnitude 9. It was the second largest earthquake in historic time. To give you another idea of the significance of the logarithmic scale of earthquake magnitude, these two earthquakes, one at 9.5 and one at about 9.3, released 1/3 of all earthquake energy of all sizes from 1906 to 2005. The fault that generated this earthquake was 600 miles long, and the motion of the fault diagonally was as much as 18 meters. This picture shows some of the damage that was done to from the shaking and the ground motion to a railroad and its bridge. The epicenter was in Prince William Sound, not too far from Anchorage, where there was a lot of damage, and not too far from Valdez. There was uplift to of the continental shelf. This is typical, and there was subsidence near the land. Here is some of the damage in Anchorage. When a town is built on unconsolidated, water-saturated sediments like mud and sand, the shaking causes liquefaction, and that can cause subsidence, which you see here. Here's some more pictures of the damage in earthquake in Anchorage. Despite the relatively low relief of Anchorage, there was a tremendous amount of damage, for example, in this landslide that you see in the upper right. Here's an example of uplift, a lot more land. And here is an example of subsidence at the little town of Portage, which has been abandoned because it went down. There was a submarine landslide in Valdez Arm, which goes northeast from Prince William Sound. It caused collapse of the harbor and docks in the port. And as the tsunami went down Valdez Arm, it was 27 feet high at this little Native American village and pretty much totally destroyed it except for that one building. There was a much larger tsunami generated by the earthquake. It was a whopping 220 feet high in a different part of Valdez Arm. And I want to point out that only 131 people were killed by this earthquake, but 119 of them died from tsunami. Most of those tsunami were triggered by underwater landslides, as opposed to the biggest tsunami, which was created by the earthquake. This is an example of tsunami damage in Alaska. So the tsunami reached, for example, Crescent City, California, about 5 hours later. It caused deaths on the beach. Its height was 75 feet, that far away from the earthquake. It also caused deaths on the Oregon coast in a couple of towns, and it caused a lot of damage in Hawaii, which is somewhere here, and in Japan. Next, we'll turn to the Sumatra earthquake, sometimes called the Indonesia earthquake, in the year 2004. The epicenter was down here at this star. The yellow circles are every place that there were aftershocks, which lasted for many months, smaller earthquakes. The shaking again lasted 10 minutes. The magnitude again was over magnitude 9. Its depth was relatively shallow at 30 kilometers. And the rupture was very, very long, over 700 miles. The maximum height of the tsunami I can't read because there's something over my screen. But the death toll is unimaginable to me. More than 200,000 deaths. Here is a Sumatra village that was overwhelmed by the tsunami. Here are some more pictures of tsunami damage. Small boats carried far inland, large boats overturned. At that time, there was no tsunami warning system for the Indian Ocean. The last tsunami there had occurred when Krakatoa erupted at sea level in 1883. But this far, like that's 8 hours after the earthquake, there were deaths in Somalia. We now have tsunami warning systems for the Caribbean Sea, the Pacific Ocean, the Indian Ocean, the USA, and Canada. Now, most of these tsunami have been caused by earthquakes, but some of them have occurred due to volcanoes, especially down in this area. Tsunami, you may have heard the one that occurred roughly a year ago in a fjord in Norway. There was a big tsunami caused by the earthquake in the 1700s in Lisbon, Portugal. So we have warning systems for for most of these places, not for example, currently for the east coast of South America, which could get a tsunami from an eruption in the Caribbean, or even a possible tsunami from the Canary Islands or some other volcanic islands in the Atlantic Ocean. Occasionally, big shield volcanoes collapse and cause a small tsunami. Finally, in terms of comparing what has happened in historic earthquakes, which might happen on the coast of Washington and Oregon, we have the Japan earthquake of 2011. The shaking lasted for 6 minutes. It was a shallow earthquake at 29 kilometers. The rupture length was less than 200 miles, which is unusually short for this big an earthquake. Basically, we had the floor of the Pacific Ocean going underneath the islands of Japan. A lot of the transportation system along the east coast of Japan was destroyed by the earthquake and also by the tsunami. I'll just show a few pictures. And along the coast of Washington and Oregon, more of our transportation is by road. We don't have a railroad there that would be destroyed, but the destruction of our highways and bridges could be severe. There was at least one dam failure during the Japan earthquake. As you are aware, most of the dams in Washington and Oregon and Northern California have been removed, but there are 3 dams left on the Olympic Peninsula. The fossil fuel risks in the Japan earthquake were severe. We have the same problem in northern Washington with all the refineries in the general area of Bellingham. So let me say a little bit about earthquake prediction, referring in particular to the Japan earthquake. There were tsunami deposits, and I'll show some pictures of these later, that had been deposited in the last 3,000 years in Japan, suggesting an 800 to 1100 year recurrence interval for these subduction zone earthquakes. Indeed, in 2007, it was predicted there would be an earthquake of more than magnitude 9.8, and it would almost certainly occur within 30 years. Also, there were some foreshocks before this magnitude 9 earthquake, which were a warning. And after the fact, there were some geophysical and geochemical phenomena which might have suggested that an earthquake was coming. In some cases before earthquakes, for example, in China in the past, there has been anomalous animal behavior, like rats coming out of the ground in the middle of winter, but that was not observed for this earthquake. The tsunami at the coast was over 40 meters high. It reached inland more than 6 miles. And here is the height of the tsunami, but this is in deep water as it crossed the Pacific Ocean and went all the way to Antarctica. This is the wave coming in one place on the coast of Japan. Very spectacular picture. This is some of the damage done by the tsunami. This airport was drowned. This ship was lifted up onto the docks. There was a lot of damage to the electrical and communication system as poles collapsed. And you've all heard about the Fukushima power plant and how that could have been a much greater disaster than it actually was. Fortunately, the only nuclear power plant in the Pacific Northwest is at Hanford. The tsunami waves from the Japan earthquake swamped Hawaii beaches and even caused damage in California. Note that this particular photo is at Crescent City, where the Alaskan earthquake killed people. The offshore topography focuses these tsunami waves in particular places. And one of those places is Crescent City, California. Now let's come back to the Juan de Fuca plate, which is actually a small Explorer plate and a small Gorda plate, and the main Juan de Fuca plate, with spreading occurring here and subduction occurring here. In the interest of time, I'm going to speed things up a little bit. I do want to say that the Cape Mendocino earthquake of December did not cause a significant tsunami because it was a strike slip fault associated with the San Andreas fault. There's lots of evidence for large tsunami generated by the Cascadia subduction zone, which reaches all the way from southern British Columbia to northern California. In many cases, those are drowned forests near the coast. When was the last Cascadia subduction zone? We knew that it had occurred from Native American legends. We were able to radiocarbon date not only some of these drowned forests, one of which you can see here at Bay Center, but also at Marsh Peak. So this was a marsh, a wetland just east of the coast, and organic matter was accumulating in it. When there was a tsunami, it swept sand from the beach over the marsh organics. So if we date the top of these organics, we can determine both from that evidence and from the drowned trees that the radiocarbon date indicates that the last major tsunami here was about 1,700 years ago. But we know more details about that particular tsunami. Dendrochronology, which I mentioned earlier, indicated that it occurred in the winter of 1699-1700. Brian Atwater and others decided, hey, there was civilization. There might have even been a newspaper that we can find. And they detected that they read that on the evening of the 26th of January in the year 1700, the Japanese had an orphan tsunami. That means that they had a tsunami without an earthquake, and it was 16 feet high. Now, tsunami velocities on the ocean are 500 miles an hour, and the travel distance from the Pacific Northwest to Japan is 5,000 miles. So we know that that earthquake here occurred 10 hours before the Japan earthquake. In other words, we know the exact date and approximately the hour that that last big tsunami occurred. Well, what is the recurrence interval? We can get that from dating deeper organics along the coast that alternate with tsunami sand. We can also look at and date and get the approximate ages of density currents caused from collapse of the continental slope and from submarine canyons that accumulate on the floor of the Pacific Ocean. Here then we have a graph from 10,000 years ago to present with the estimated magnitude of earthquakes from 7 up to 9.5. Here is the big one that occurred in the year 1700. And we look at this chart and everybody asks, when is the next big one going to occur? Nobody knows. It's a matter of not if, but when. One estimate in the year 2021 by the Washington Geological Survey estimated a 10 to 17% chance that the next big subduction zone earthquake would occur in 50 years. One of many USGS estimates is that there is a 37% chance in the next 50 years. What is going to happen during that earthquake? Modeling indicates that, as you saw for the Alaskan earthquake, there will be a zone offshore which will rise, and there will be a zone near the shore which subsides. One model predicts that this subsidence is going to be about 6 feet. There's the coast right there. Another analysis by, again, the Washington Geological Survey in the year 2021, 4 years ago, was that the uplift would be as much as 49 feet, and the subsidence would be as much as 13 feet, and some of that subsidence would be near our coast. Here is a model of the earthquake shaking, the land going down 6 to 12 feet, and the tsunami coming in and inundating the land. In other words, the tsunami would cause more damage because the land had subsided exactly when the earthquake ruptures, and the tsunami would roll in minutes later, maybe 20 minutes later. So what are the risks of the next subduction zone earthquake on the coast and also inland? We would get subsidence and liquefaction. I talked about liquefaction in connection with the Alaskan earthquake, landslides and debris flows, death and injury. What would we do with those folks? People would be missing. There would be damaged buildings, many homeless, damaged critical structures, downed utility poles. Transportation would be a problem because of damaged vehicles, roads, bridges, and airports. There would be problems with communication because of the loss of power, and batteries don't last forever. As in the case of the San Francisco earthquake, there are likely to be lots of fires. Fire stations would be damaged. Broken water pipes would reduce water pressure. There'd be a lot of animals to deal with. There would be, as time goes by, a lot of waste disposal, not only from the earthquake and tsunami, and there would be saltwater intrusion of freshwater sources. Mike Jenkins, a Whitman student, Susan Hubbard Sakamoto, a Whitman alum, and I wrote a paper in 2007 dealing with tsunami-induced contamination of water resources with the potential of the salt water getting into the fresh water supply. And would be affected as far east as Walla Walla, with refugees seeking places to live. Well, all is not bleak. A lot has been done by governments. There are marked evacuation routes. There are emergency warning systems. Information is being distributed to citizens and tourists. If the tsunami is far away, like coming from Japan or Alaska, then it'll take a long time to get here. If it's a local earthquake from the Cascadia subduction zone, the shaking is likely to last 5 minutes. The tsunami will come within 20 minutes. So if the water recedes rapidly, and or certainly if you feel shaking within for 15 seconds or less, get to high ground as fast as possible. Washington Geological Survey is making walk time maps for coastal communities, so that, for example, if you felt the shaking right here, it would take approximately 30 minutes to get to high ground in the area of Queets on the Washington coast. New schools are being built above tsunami height. Critical structures like fire stations are being strengthened. City governments are requesting funds to build critical structures at higher elevations. In some cases, those bonds did not pass. For example, here's a town with a fire station and a police station at an elevation of approximately 10 feet above sea level. This school was moved to the east into the coast mountains. Residents and tourists also should have go bags which have emergency supplies in case there is an earthquake and you've got to eat and you've got to get in contact with people. You need water to drink, etc. We need more tsunami towers. This is an example of one which had platforms at 40 and 50 feet and has a capacity of at least 400 feet. Obviously, they need to be built above tsunami height, and they need to be in proximity so that people can get there quickly. Unfortunately, coastal communities are still issuing building permits on land that is less than 10 feet above sea level. In many cases, this is water saturated, unconsolidated, organic rich, fine grained sediment that is going to subside, that is likely to have liquefaction, and that will be inundated by tsunami. One particular person that intends to build here, right next to a creek that is barely above sea level, cut down 5 Sitka spruce for his building site. So we've talked about what's going to happen on the coast. What's going to happen? I want to finish up with what's going to happen in Puget Sound if there is a Cascadia subduction zone earthquake. Magnitude 9, severe shaking on the coast, pretty bad shaking and a lot of damage in the Puget lowland. We may feel a Cascadia subduction zone earthquake in Walla Walla. The tsunami will travel from the Pacific Ocean east along the Strait of Juan de Fuca. It'll take about 1.5 hours to get to Whidbey Island. The San Juan Islands are likely to have some of the highest waves. The waves will get lower as they propagate up the Strait of Georgia and down through Puget Sound. The waves will take about 2 hours to get to Seattle, Tacoma. The waves are likely to be 10 feet high further south. Remember that the tsunami is a wave. We will get alternate waves and retreat so that these places will empty. Commencement Bay at Tacoma is likely to get the wave about 3.5 hours later. The waves can last as much as 14 hours in Puget Sound. There will be, in places, very strong currents for more than a day. I want to emphasize the fact that if the high tide happens to be high, there will be more damage from such a tsunami. Whereas if there's low tide, there'll be less damage, but more ships will at least temporarily be grounded. Now, these two comparisons are for Puget Sound. They are not for the coast. They are for the Puget lowland. The magnitude 9 earthquake at the coast will give us a 2-hour warning time for tsunami. There will be little or no uplift or subsidence. The damage will be widespread, but will be lesser. In contrast, if the earthquake occurs in the Puget lowland, although it will be smaller, there will be no warning to speak of, only minutes for a bigger local tsunami. There will be local uplift and subsidence, and there will be more local damage, but not as intense. Thank you very much. I'll take questions.
If you've got a question and would like to turn on your microphone and ask Bob, I see a couple people.
I'll ask a question of Bob. Fritz Paulus here, Bob. Hey, I live in Portland, but I imagine the shaking would be similar here as in Seattle and such. How much damage do you think there'll be to like a typical homes here?
I think, but I do not know, that the minimum will be breaking of masonry chimneys. I think that the shaking is very much amplified if you're sitting on floodplain sediments as opposed to sitting on bedrock, or for the Puget lowland sitting on lodgement till deposited by glaciers. So I think that as far east as Seattle and Portland and Eugene, that shaking will damage some masonry buildings. I hope that stick buildings will be okay, but I do not know. I'm not an engineer.
Yeah. But does bolting your house down to the foundation help then?
I have a cabin on Hood Canal, and I bolted it to the pier blocks, which are set on very compact sediment.
Okay. So if you have a stick house with a chimney that's kind of on the side, that could maybe be a weak point, possibly.
I think so. The as I said before, the magnitude 6.5 earthquakes in the Puget Lowland damaged a lot of chimneys and some buildings.
All right. What about just like in the just typical bridges? Do you think, like for example, that Portland's got 10 different bridges that cross the Willamette River. Do you think those are not going to be standing? I know you're not an engineer, but
Again, I'm not an engineer. My guess is that most of the bridges in the Portland and Seattle area will survive, most of them. I think that most of the bridges along the Coast Highway 101 will collapse.
yeah. Okay. All right. Hey, thank you, Bob.
Thank you.
Kate, would you like to unmute and ask your question?
Great. Hey, Bob, thanks so much for this. Really appreciate it. And so I have a question related to the tsunami prep and the amount of subsidence that's happening. So when there's consideration of elevation, there's elevation before there's subsidence, but then if there's the earthquake and land drops down and then the tsunami's coming in, how is that being taken into account, both for planning, but then also how is that being communicated, to members of the public? So, if somebody's thinking, oh, I'm at, I'm 30 feet above sea level, I'm fine. But if, is it being communicated to them that they might not remain 30 feet above sea level?
I think that some communities are having town meetings and communicating very well to their residents about the fact that there may be 10 feet of subsidence followed by a 40-foot high tsunami, which mean that the water level would come up to 50 feet. We really don't know how high the tsunami is going to be. If you have another question related to that, go ahead and ask it. But first, I want to say something that I forgot. I meant to say at the beginning. My environmental geology class at Whitman had a nickname, the disaster course. In 1999, I was asked to give the commencement address. The convocation address. I focused on global climate change. It was not a happy convocation address. Unfortunately, individuals and governments have done very little about climate change. We had hoped, according, for example, to the Paris Agreement, that we would not exceed 1.5 degrees Celsius over the pre-industrial temperatures. In 2024, we reached 1.5 degrees Celsius because we have not done anywhere near enough. We have probably years, maybe decades, to do something about the next Cascadia subduction zone earthquake. Will we? Thank you for that little addition, folks. Did you have any more questions?
Well, it's a related question in terms of the preparedness. It's terrific to hear that some of the coastal communities are really coming together as communities and doing the community-based planning for it. I think is Shake Alert available in Washington as well as it is, I know, in California where I am, and how much is that sort of getting tied into emergency alerting, part of the preparedness that's happening?
I don't know about the answer, but I think that if you have a smartphone, you can get an earthquake alert.
Great. Yeah, that sounds like Shake Alert.
I don't
Terrific.
have a smartphone.
Congratulations.
Thank you.
Great. Thanks, Bob.
Thank you, Kate. Ethan, you're up next, but first I have something from the chat. This is from Ted Watts, who wants to know, is the placement of 2 stadia in the SoDo area of Seattle a sign of engineering and geological hubris?
I'm pretty sure that most new buildings in cities, and just basically in Western Washington and Oregon. I mean, we have an earthquake code in Walla Walla. And we had a magnitude 6 earthquake in 1936, which broke some chimneys. So the tsunami in Puget Sound, even, well, if the earthquake is right there in Seattle, you're going to get some inundation of those structures. But if the earthquake is to the north or to the south, the tsunami will probably only be a few feet high. As I already said, the tsunami from a Cascadia subduction earthquake is probably only going to be about 10 feet high. There is, I don't know at what depth, but there is till. There are very strong glacial deposits in parts of Seattle. I expect that those engineers know what they're doing, Ted.
Thanks. Appreciate that, Bob. Okay, Ethan, you're up next. But you got to unmute yourself. Uh-oh.
Sorry, is that better?
There you go.
Wrong microphone selected. I was unmuted. Apologies. Bob, thank you. This was a wonderful return to Northwest geology for me, and I genuinely enjoyed it. My question is with respect to magmatism in the relationship to earthquakes of this magnitude. So, for example, along the Cascadia subduction zone, with a magnitude 9 earthquake in this convergent setting, would we expect that to correlate to or initiate any volcanic activity? And has it done something like that in the past in similar geologic settings?
I talked about the only example that I know of earthquakes related to volcanoes, and that was the one in Chile, which erupted 2 days after that largest earthquake in historic time.
Yeah.
There is, you didn't ask this question, but there have been some papers that have come out in the last few years that relate the Lisbon earthquake, which is the largest historic earthquake in Europe, and which somebody, I'm sorry, I don't have the date down. It might have been 1756, but the largest earthquake to ever occur in eastern North America was at Cape Ann, Massachusetts, and it was 2 weeks after the Lisbon earthquake. So some geophysicists think that the shaking in Portugal caused a little bit of a slip or a big slip at Cape Ann. You know, if you have an inclined plane and you put an object, you put a block on it, if you shake that inclined plane, that block is likely to slide off. So you can see how shaking one place might cause motion elsewhere.
Thanks. That would be really impressive given the number of faults and fractures and different plates in between those two settings, but I didn't know that. Thank you.
Art, would you like to go ahead next?
Yes. Again, thanks very much for the presentation. I was a general contractor during the Nisqually Glacier, and I got called to a house in central Seattle. And the description was the chimney had fallen down. There were 6 chimneys in one block that were on the ground. So just as an example of what can happen, and that wasn't a huge earthquake. My question is—
Thank you for that.
I live on Whidbey, on the east side of Whidbey Island, with a Cascadia subduction zone earthquake. What kind of evidence, historical evidence, is there, and what prediction would there be for tsunamis coming into Puget Sound, and what kind of wave height would we be looking at if there was a major tsunami in Puget Sound?
Gotcha. Carl Wegman, if you know the answer to this, please pipe up after I say something. To the best of my knowledge, there is no evidence for tsunami deposits or related to a Cascadia subduction zone earthquake. I have heard that there are tsunami deposits on the south end of Whidbey Island from the earthquake in the year 1700. Let me think. No, not 17. The earthquake in AD 900. That caused the uplift at Restoration Point. I'm told that there are tsunami deposits associated with that Puget Lowland earthquake, but I have not seen them.
Okay.
Charles, you're up next, and then I've got a couple in the chat.
There, finally. Bob, thank you very much. I've enjoyed this. There was a book that was published maybe 10 years ago now about what would happen if the Cascadia subduction zone earthquake happened sort of offshore from Portland. And there was an item in that book that suggested that nearly all of the freeway bridges that cross the various rivers and inlets in Portland would come down during such an earthquake. You haven't appeared to present the Cascadia subduction zone earthquakes as being quite that drastic. So I'm just curious, you probably read that book and you might have some responses to it.
I read a novel in which scientists at Oregon or Oregon State predict an earthquake, but I don't think I've read that particular book. One of the things I want to point out is that when the Cascadia subduction zone ruptures, it is likely to be from southern Vancouver Island all the way to Northern California. So it may not matter whether you're in Portland or Seattle. There is one scenario, and I can't give you a reference to it, in which some scientists think that it could rupture separately, the north half at once and the south half at a different time. And if that happened, the earthquakes would probably only be high 8s instead of low 9s. I was asked earlier about bridges in the Portland area, and I said, I'm not an engineer and I don't know, but I expect most bridges in the Willamette Valley and the Puget Lowland to be okay.
That brings us to another good question in the chat. Would a Seattle fault episode risk failure of the I-90 bridge, and I guess the 520, through anchor separation or water level change, or both?
The I-90 bridges east and west of Mercer Island in Seattle were built a long time ago. And if that is a magnitude 7.5 earthquake, such as occurred in AD 900, I would expect those bridges to fail. If it's an earthquake that is around 6.5, like those that occurred in Tacoma, Olympia, and Nisqually, I think, even though the earthquake would be closer, that is in Seattle, I think those bridges might survive. Again, I'm not an engineer, and I really can't give you very good answers.
We like your guesses. That's okay.
I'm sure
I've got-
that city planners are thinking about it.
Yeah. Another from the chat. Your maps of the Pacific Ocean showed radiating lines extended from the earthquake radiating out across the ocean. How much is the wave height reduced or the energy reduced for every, say, 100 miles of travel of those waves?
Okay. The particular map that you are referring to, I believe, was from Japan, with the tsunami going east to the Americas, south to Antarctica, and southwest to islands south of Japan. Those elevations were in, I believe, centimeters. When tsunamis are in deep water, they can be detected by satellites. They can be detected by special buoys, which are scattered all over the world as part of the tsunami warning system. The wave is typically a meter high. If you were on a ship, and the wavelength is hundreds of kilometers. So if you're on a ship and you're not even going to be able to feel the tsunami. So again, roughly a meter high. But when that tsunami starts to feel even the continental slope, and then especially when it gets onto the continental shelf, it slows down and it gets really high. Does that answer your question?
Yes, thank you, Bob.
Jeff, would you like to unmute and ask your question?
Yeah, I have a comment and a question. The earlier question about the stadiums in downtown Seattle, I once read that those are built on pylons that go down to the bedrock down below. They do not rest on the soil at the surface at all. And those are very, very complex construction projects. My question is, are you familiar with the Japanese earthquake scale that measures the intensity at the surface, not the magnitude at the epicenter? It's a very different scale that measures how strong the earthquake people feel, and also it gives much more credence to how shallow the earthquake is.
Okay. You brought up three things, so let me know if I forgot one of them.
Okay.
The Seattle Fault has been moving for millions of years. If you go north of the Seattle Fault, you find very deep sediments that have been accumulating for a million years, not just the glacial deposits from the last 2 million years. If you go south of the Seattle Fault, bedrock is very close to the surface. For example, there's bedrock to the west at Restoration Point. There's basalt bedrock at Green and Gold Mountain on the Kitsap Peninsula. So south of Seattle, it is possible to put pylons down to bedrock. They're more likely, if they get till, lodgement till, which was compacted by thousands of feet of ice, they're likely to stop at the till. And north of Seattle, they can also stop at the till. But north of Seattle, there's no way you can put pylons down to bedrock because it's hundreds or thousands of feet down. Anyhow, but you can put a lot of concrete down there in addition to the pylons. So your point is that probably those stadiums are very safe because of the pylons. They probably did not reach bedrock, but I don't know. The next thing I want to point out, and you mentioned this, is that shallow earthquakes are much more damaging than deep earthquakes for the total amount of energy released. The other thing that you mentioned is the Mercalli intensity scale, which is used all over the world and has been used long before the Richter magnitude scale developed. Basically, and it's usually in Roman numerals. Basically, it starts about 1, which means barely felt. You get up to 2 and 3, teacups rattle. And you get up to 5 or 6, damage beginning. You get up to 10 and there's widespread destruction. You get up to 12 and everything's as bad as it could possibly be. But I'm not sure that's the intensity scale for Japan, but it is a worldwide intensity scale that has been used for approaching at least 150 years.
Now, the Japanese scale runs a little bit less than the Richter scale. So like the Sendai, the Tohoku earthquake in Japan might have been a 9 on the Richter scale. It comes into about 8 on the Japanese scale.
Okay, I'm not familiar with that scale.
They have amusement park rides, or like rides that you can buckle yourself in, and they will give you a scale you up from a 1 up to about a 10, and so you'll know how hard the earthquake is. It's quite interesting.
Sounds great. Let's have one in Western Washington to help people prepare.
Okay, thanks.
I'm going to go back to the chat now. Let's try and bring some hope into this, okay? As a geologist, how do you cope with climate anxiety, and what reassurance, if any, might you be able to offer us?
I can't answer that without getting political, and I don't want to get political. So I except to say that some people get very depressed when they think about global warming and associated forest fires, snow and ice melting, acidification of the oceans, drought, floods. Climate change can be overwhelming, and we must do more.
Another from the chat. Would you see a tsunami on the Columbia River up to Bonneville Dam, basically at sea level over 100 miles from the coast?
Thank you. A tsunami that's 40 or 50 feet high at the mouth of the Columbia River is going to get damped by the big sandbars in the general vicinity of Astoria, the ones that make the Columbia River known as the graveyard of the Pacific. And I do not think that there would be any tsunami at all as far east as Bonneville Dam. And I don't think it would be very high in Portland because of the damping at Astoria.
Thank you. Here's a question from Shannon Smith, has a statement in front of it. Recently, I read that NOAA, the U.S. Geologic Service, or geology departments of our Northwest universities, for the first time mapped and placed deep water measurement devices underwater, either within or next to the fault, to track and collect real-time specific data regarding movements, etc. Would deep water measurement of the fault changes help to inform earthquake predictions?
Shannon, I do not know the answer. They'd have to be very sensitive. The fault is locked, but if they put seismometers out there near the Cascadia subduction zone, it's going to help to determine micro earthquakes. And technology is getting better all the time. We're very good at predicting volcanic eruptions. We are lousy at predicting earthquakes, but things are getting better.
All right, looks like 2 more questions live. Is Shannon, would you like to unmute and ask your question?
Hey, I already did. So Jennifer, I wrote it in the chat. So
Okay,
hi, Bob.
perfect.
I'm the gal
Perfect.
that actually lives right next to the creek at 7 feet above sea level there. So I will actually offer that our town, even though we do like earthquake preparedness and disaster preparedness quite often, most folks in the Oregon coast are still woefully unprepared. And the Washington coast too, I think, for real understanding, because it's been so long since a major earthquake, and even the little small tsunamis we've had warnings about. We've not been too proactive or proactive enough to prepare for what Bob has described as the potential risk ahead. So thank you, and we hope climate change will be addressed soon by someone. So thanks,
Thank
Bob,
you, Shannon.
and everybody.
Marcus, you've had your hand up patiently. Would you like to ask your question?
Yes. Hi, Bob. So I vividly remember the Nisqually earthquake. I happened to be at a manufacturing plant that day, right on the Hylabos waterway in the port of Tacoma, and it was impressive. And I'm curious if you could speak about the details of that earthquake and why that one didn't cause a notable tsunami, and what's the likelihood of having more of that type of earthquake versus the type that would cause a tsunami in Puget Sound over the next 50 years.
I don't know if there was any surface displacement from the Nisqually fault. I don't, from the Nisqually earthquake, I don't think there was. So if you don't get displacement underwater, it can't just be land displacement, like on the Saddle Mountain East fault that I talked about. It has to be vertical displacement from a normal or reverse fault underwater. If the land goes down under the water, then if you're on the nearby shoreline, the water goes out. If ever the water is going out, that means run for the hills. Okay. But if the land goes up under the water, then the first thing that happens is a big wave comes at you. If the fault is underwater and one side goes up and one side goes down, there's still going to be a tsunami, and it may go down in one direction and up in another.
Is there?
Go ahead.
That's great, and I understand that. I'm curious what you think about the likelihood of an underwater earthquake causing a displacement then versus the type of earthquakes that are land based or land focused and in that Puget Sound area. Like
the Seattle fault is goes under Puget Sound. It's right here on the map that's still showing. For reference, here's the Saddle Mountain East fault. And so this side's going to go up and that side's going to go down. And as I showed before, it's likely that that magnitude 7 or so earthquake that's going to happen, because we have records of them happening for the last 3,000 years. It's going to cause a tsunami of, wild guess, 20 feet high in Seattle and 10 feet high in Tacoma.
okay. And just one other question. Are you familiar with Table Mountain along the Columbia River near Stevenson? It's you know where Cascade Locks is? There's that Table Mountains where a pretty significant chunk of the mountain broke away and there's a large landslide and it kind of disrupted the path of the river a bit.
Yes, that's called the Bonneville Slide.
Yeah.
And it is east of Bonneville Dam and goes all the way east to Wind Mountain.
Right. What caused that? Was that an earthquake?
There have been many, many papers written on the age of the Bonneville Slide. Some people have argued that it did occur in AD 900, that it's 1,100 years old. Some people have argued that it is much more recent. I've never heard anybody say that it was a connection with the 1872 earthquake. There are postcards showing standing trees in the Columbia River before it was dammed that were drowned and killed by a temporary rise of water as the Bonneville Slide dammed the Columbia River and made a temporary lake. It killed the trees. So I don't know what the latest is on that temporary lake from the Bonneville Slide, which moved from the low mountains in Washington right there and came all the way across and dammed the Columbia River and led to the legend, the Bridge of the Gods.
So it's not really known then what the actual cause was.
Well, the cause is, I know the cause. The resistant rocks on both sides of Columbia River Gorge are Columbia River basalts, which are 17 to 6 million years old. Underneath them are sedimentary rocks that are full of ash that are relatively impermeable and relatively weak. The dip of the rocks, the direction in which the rocks are going down is to the south. So that means that we have rocks that are soaking up water, the joints in the Columbia River basalt, percolating through the basalt down to the relatively impermeable, weak, older rocks that are beneath. And there's a dip to the south. And so water saturation, possibly associated with an earthquake, caused the whole mess to slide and collapse to the south, damming the river. The
Thank
same
you.
scenario does not exist on the Oregon side because the dip is, we have the same body, we have the same rocks, but they're dipping to the south. They're dipping away from the Columbia River.
Interesting. Thank you.
All right, I just have some quick closing comments here. Thank you so much, Bob, for being here with us, and thank you all of you for joining us today. I want to touch briefly on something I mentioned in the introduction, and that is the Bob Carson Outdoor Fund, or more particularly, the Bob Carson support of our outdoor program on Whitman campus. The outdoors have been an important focus for the college for decades. There was an outing club in the early 1960s. The current outdoor program was established in 1975 and offers trips and recreational opportunities that allow Whitman students to get outside and explore the natural beauty surrounding Walla Walla and other wilderness areas. Things like kayaking, hiking, mountain biking, rafting, skiing, snowshoeing, ice climbing. The possibilities are nearly endless. The Bob Carson Outdoor Program Fund was created in 2012 through gifts from two of Bob's former students, and it gives the opportunity for students to participate in outdoor trips, regardless of the ability to afford the cost of that trip. And specifically, the fund allows every student to participate in at least one free outdoor program trip every year that they are at Whitman. About 5 years ago, Bill Montgomery, class of 61, who had been in the original early 1960s outing club, made a significant gift to begin endowing the fund, extending opportunities for students to take advantage of the opportunities available to experience our region up close and personally. And more recently, two alums, Charlie and Patty Hinkle Nelson, established the Bob Carson Outdoor Program Endowment, providing permanent support for the fund. Their aspiration in making this gift was to enhance funding towards the goal of providing an outdoor program adventure per year for every student, while also recognizing the contributions of Bob and Claire. There are many benefits to the outdoor program trips: an opportunity to learn about safety in the outdoors, gaining new leadership ability, participating in new outdoor sports in places you've never been to, learning about nature and the magnificent environment of our Pacific Northwest, meeting new people. Many students learn a lifelong activity, and even more, build their community of lifelong friends from the people that they meet in the OP. We will be hosting an March 13th event with Bob in person and Brian Sheedy, director of the OP. And if you would like to participate, please let us know. I've also included the link to more information about that in our chat. And you'll probably get an email just to let you know that that opportunity exists, but we'd love to have you join us. You can contact either Jamie Kennedy or Steve Setchell if you'd be open to a conversation about learning more to support the OP. Again, thank you all for joining us. And Bob, thank you so much for spending some of your time with us. I hope to see you all soon in person.
Thank you all for participating.